Alright guys, hello everyone again. So now today we're going to discuss drag. So drag is, in the earlier video I mentioned, drag is an aerodynamic force that is parallel to the relative airflow and opposite in direction to the flight path. Correct. So now drag, this video will have discuss drag in specific way. Last video we had coefficient of drag. So now drag is divided into two types. Alright, so that is parasite drag and this is induced drag. Alright, and parasite drag is divided into two types again: profile drag and interference drag. Alright, and profile drag is again divided into two types, that is form drag and skin friction drag. So we are going to discuss one by one each of the meanings. Alright, so we'll start with parasite drag. Now one key important point I want you guys to know is parasite drag is a non-lifting drag. Induced drag is a lifting drag. So basically this drag is caused due to creation of lift. When lift is generated, induced drag is there, and parasite drag is anyways there. It doesn't is irrespective of the lift generated or not. Alright, so now first we'll discuss form drag. Okay, so form drag, it's the simplest of all. It is due to the shape or profile of the body. So form drag can basically be reduced but cannot be, like, made zero. Alright, for example, let us take, so that it's easy to understand, say a surface is taken. Alright, so now this is providing total 100% drag. Alright, it's a rectangular plane, basically rectangular plate or plane, whatever it is. Now if the same volume is made into a shape of a sphere, so this here it becomes 50% form drag, so it reduces, as you can see. So basically it's due to the shape or profile of the body. Now you will be surprised to know that this is 100%, right? Something of an aerofoil shape gives only 5% form drag. As I said earlier, you cannot delete it, but you can reduce it by streamlining the foil. Alright, so aerodynamically streamlining, shaping the foil can reduce form drag. Alright, so this is form drag. Now we'll discuss skin friction drag. Skin friction drag. Alright, so this is basically, like, I'll just draw the figure so that it's easier to understand. Alright, okay, so in the earlier videos also, if you remember, I mentioned this is called the stagnation point. Alright, stagnation point, and this is your transition point, and this point is called your separation point. Okay, and this is your laminar airflow, this is your turbulent airflow. Now these points are important to remember. Stagnation point is where the velocity is 0 but the pressure is maximum, alright. It hits and it stagnates there, and then it splits into upper and lower parts of the surface of the aerofoil. Transition point is where from the laminar airflow, smooth airflow, the airflow turns into a turbulent one, alright. And separation point is where the airflow separates from the wing and it resumes normal. That is basically a downwash kind of a thing, alright. So here the airflow becomes normal, alright. So the exact definition I'm writing here: skin friction drag is due to retarded boundary layer in contact with the aircraft skin, alright. So basically it is a factor depending on the smoothness of the aircraft surface. The more the smooth the surface, skin friction, right? So the lesser the if you want less friction, you smoothen the surface, alright. So that is skin friction drag. Now there's something called as interference drag, right? Interference drag, alright. So interference drag is the drag due to the joints, alright. Drag due to joints. So joints as in, like, where there's a wing fuselage joint is there, the wing root into the fuselage, etc. It is a drag created due to the joints. Example are wing fuselage joint, that is basically the root of the wing joining the fuselage. Then there is wing engine joint, right, where the engine is mounted on the wing, that is also a joint. So, and that is called nacelle, alright. So basically interference drag is the drag due to the joints, and it can be prevented by smoothening the joints, alright. So you smoothen the joints, you'll reduce the interference drag. So if you remember, interference drag is also part of the parasite drag. So we have discussed form drag, we have discussed skin friction drag and interference drag. So that is done with the parasite drag. Now we'll write down the factors that are affecting parasite drag. Parasite drag, factors affecting it. Okay, so first point is your IAS. Simple. Parasite drag is directly proportional to square of the indicated airspeed. If IAS is doubled, parasite drag increases 4 times. So at the higher speeds, like if you increase it 5 times, 6 times, the ratio is much higher, alright. Shape. Okay, so basically if you have a streamlined profile, like streamlined aerofoil profile, streamlined aerofoil will have less parasite drag, alright. Third one is surface smoothness. Surface smoothness, more the smoothness, less the skin friction drag, basically, which is a part of a parasite drag, alright. Next is your surface area. Surface area. If you increase surface area, your parasite drag will also increase, because you're providing it more surface and you're providing it more the air more area, so you have more surface smoothness might be less, or depending on the smoothness of the surface, you're providing more area basically, or increasing parasite drag. Alright, configuration of the aircraft. So simple is add flaps, landing gear, etc. Increase parasite drag. You may be surprised to know that parasite drag almost increases by as much as 80% due to flaps, gear, slats, etc. Alright, now altitude. So this is important point to remember. Parasite drag is not affected by altitude. Now the reason you might want to know is, like, generally when you are flying, it will be flown at a constant IS, or the dynamic pressure will remain constant, and this means that the parasite drag is not going to be affected, because at a higher IS your TAS also will be higher for a higher altitude. So altitude, parasite drag is not affected by altitude. Angle of attack. Again, angle of attack does not affect parasite drag. Alright, so angle of attack does not affect parasite drag. So these 2 points are important to remember. Others are just as simple as you can think of. Parasite drag is indicated airspeed square. Alright, so now we'll discuss induced drag. Alright, before that I'll just draw a simple figure so that we can remember parasite drag in terms of velocity. Alright, so this is your, say, velocity, and this is your drag. So parasite drag will increase like this. This is parasite drag. Alright, so with increasing velocity, as remember I mentioned, parasite drag is a square of the indicated airspeed. So as you increase the velocity, your parasite drag will increase. Alright, so now we'll discuss induced drag, which in the earlier video we had discussed about induced drag. Alright, so similar one, we'll just do a quick recap so that it's part of drag only, right? Induced drag. This is due to the wingtip vortices. I'll do a quick recap. Please refer to the previous videos for knowing more details about it. And trailing edge vortices. Alright, so I'll just read out so that it's just a recap. Wing vortices are due to high pressure air below the wing spurling over upwards and outwards at the wingtip towards the low pressure area on the upper surface, and the airflow movement is clockwise and anti-clockwise on the right wing and clockwise on the left wing. So this is the wing if you see from behind. Alright, so and the air on the left wing, say this is the left wing, right? So we'll have a clockwise movement towards the root, and here you'll have a anti-clockwise on the right wing. So this is wingtip vortices generated. Alright, and trailing edge vortices is basically when the airflow over the wing is inwards and towards the fuselage due to low pressure on the top surfaces and outward on the below surfaces, resulting in conflict meeting at the trailing edge, causing induced drag. This is also wake turbulence. Basically this is wake turbulence. I have mentioned wake turbulence in the previous video, so just go there for the reference. This happens at the trailing edge. Basically suppose this is your wing. Alright, so this is your trailing edge, right? So generally when you have a span wise differential, so on the top it will be like this, and on the bottom of the wing it will be something like this. alright, outwards. So at this point here there will be a conflict of the airflow, and this is called the trailing edge vortices, and this is basically wake turbulence, too easy to understand. Alright, now we'll discuss factors affecting induced drag. Alright, so this is important. This we didn't discuss in the previous video because it wasn't required that time. Now we'll discuss it here. Few points you might want to note down. Alright, so induced drag, I'll use ID here, okay, is inversely proportional to indicated airspeed square. Alright, so more the speed, less is your induced drag. Alright, second one, induced drag is proportional to 1 by aspect ratio. Alright, this is aspect ratio. So higher the aspect ratio, less is the induced drag. Now why is this? Alright, so aspect ratio is like when you have a aspect ratio is suppose say high, that means your induced drag will be less. So a high aspect ratio means wingspan is high. Alright, so that will give you less induced drag. Theoretically, on a wingspan of say theoretically this is wingspan is infinity, induced drag is 0, right? And higher aspect ratio wings are therefore more efficient. Third one is induced drag is directly proportional to the lift square. The more the lift, more the induced drag. Alright, and because if you can see, when this happens during the takeoff, landing, roll, and so on. So when lift is generated, induced drag will be increasing. Then we have induced drag by load factor. Alright, so we'll just sum it up into one equation so that you can remember. So this is the equation, I'll just write it down. ID lift square load factor 1 by IS whole square and 1 by aspect ratio. So with this you can solve any sort of problem given to you. So if somebody asks you what happens to a IS squared, what happens to induced drag, it reduces. Alright, so on. Now we'll discuss few formula related to induced drag coefficient, that is also important as well. So it is given by CD of I, coefficient of drag, induced drag. It is given by a specific formula, coefficient of lift square by your aspect ratio. Alright, so this is your lift coefficient of drag, induced drag. Now this is substituted into basically induced drag formula, that is your C di half rho v square s, where the same values remain. V is your TAS, rho is your density, s is your surface area. Only thing that changes is your coefficient of induced drag, and this is the formula for coefficient of induced drag. Alright, so if you just see, if speed is increased 4 times, alright, speed is increased 4 times, then to maintain constant lift must be decreased 1/4 times of the previous value. So it's just that using these equations we can find out how much drag is generated. Alright, now we'll discuss methods to reduce induced drag. This is also an important segment, so just pay attention. Alright, methods to reduce induced drag. Alright, simple ones are wing end plates. I'll just write down first, then we'll discuss wing tip fuel tanks, winglets, wingtip shape modifications, then we'll discuss something about boundary layer, so that that will give you a, first we'll discuss this, then we'll discuss boundary layer. Alright, so wing end plates are basically at the end of the wing. Say we'll just draw the wing like this. Alright, so you have protruding wingtip plates, wing end plates basically. It may be up or down, depends on the design of the manufacturer. Wingtip fuel tanks, so you'll have a fuel tank like this at the end of the wing. Alright, so this will also help in reducing the moment, root chord moment. And wingtip fuel tanks will also reduce induced drags, because the wingtip vortices won't be able to meet the airflow from the above. Winglets are also specific design. They are something like this. Alright, so this is the wing, this is the aeroplane, this is the wing. I've drawn it a little big. So this is wingtip winglets, usually seen in the 737s and all. And wingtip shape modifications is part of this in this, so that some have smaller modifications done. They have winglets, wingtip, etc. Alright, now there's something important we'll discuss is boundary layer. Alright, fifth one is your boundary layer. Now basically induced drag, if you trailing edge, this technique is for trailing edge, reducing trailing edge vortices. Alright, so we have three procedures in this: wing fences, vortex generator, alright, and C is your slotted flaps. So when in the earlier page, one second, let's explain. If you remember saying this, if we delay this transition point further beyond somewhere here, then your induced drag reduces. Alright, so basically delaying the position of the transition point will help us reduce the induced drag. So using these wing fences, vortex generators, slotted flaps, we can just move the transition point beyond a certain value so that the induced drag is reduced. Now how? We'll just see. So there's something called as vortex generator. These also help in avoiding span-wise differential. Alright, so first we'll discuss slotted flaps. So slotted flaps is something like this. Suppose this is the wing. These are flaps that come ahead, basically slats. Alright, slotted flaps, they have slots in between them. So this is your slats and this is your slot. So when the air comes from here and it goes, this re-energizes the boundary layer, and hence the separation happens at a delayed point. Generally it might happen here, but due to this it re-energizes the boundary layer and it separates at a later stage, and thus reducing induced drag. Alright. Right, so the next one we are going to discuss is wing fences. Alright, so say let us take this is the wing. Alright, so wing fences are some, say, triangular features on the upper surface of the wing. So when airflow is generally flowing, it will flow straight through, and we have studied earlier that there's a movement towards the root on the upper surface, right? So what these wing fences do is, these are triangular structures generally. So when the air flows and tries to move towards the root, they do not allow that, and the airflow continues straight forward. So this avoids the trailing edge vortices basically. So wake turbulences reduce, and obviously the induced drag is reduced. This is your wing fences. Alright, now there's something called as vortex generators. Alright, so vortex generator is this. Alright, so generally when the air is flowing, you'll have a separation here, for example, and this is your vortex generator. So what this does is, suppose the air is flowing here through this part of the aerofoil, the transition point moves backwards. Now this movement of transition point will obviously reduce your induced drag. Alright, so this helps in moving the transition point, the vortex generator, and this is also helpful. And this is the graph for the induced drag. Velocity increasing, drag increasing, and the induced drag movement is something like this. Alright, this is your induced drag. Now if you remember, we had discussed parasite drag graph as well. I'll just show it to you for a minute. So the parasite drag had moved. So now what I'll do is try combining both of these graphs, and we'll try to interpret something important out of it. Alright, so okay, so velocity and drag. So here is your parasite drag, and here is your induced drag. Okay, and the resultant of these both is something like this. Okay, so now if you can see, I'll just write down, this is your induced drag, this is your parasite drag, and this is your total drag. Now if you can see, they are intersecting at a particular point. Alright, so this point is crucial for us, and it is called as VMD or VBR. If you can see, it's also it's almost coinciding with the minimum point of the total drag. So why is this important? This specifies that at this point the drag is least. As you can see in the total drag curve as well, the drag is least, and at this also the parasite drag and induced drag is at the intersecting point and is at the least. Alright, so now this is called as minimum drag speed, VMD, or best range speed or velocity, that is VBR. Now if anything beyond this line, this velocity is flown, the drag will increase. Suppose you fly in this region, this velocity, your induced drag will be more. Though your parasite drag is less, but the drag, overall drag is high. If you can see, the total drag is high. And if you fly in this region, that is higher velocity, your induced drag will be low, but your parasite drag will increase. So your total drag again will have a higher value. So as you can see in this. Alright. So similarly, we have VMD. I'll read down a line. The speed VMD is an important reference for many items of an aeroplane, like performance, range, endurance, climb, glide, maneuver, landing, and takeoff performance. Alright, so that's all about drag. In the next video, we shall discuss stall, or maybe I'm thinking of doing ground effect and high lift devices. Alright, then keep watching, share it, like it. I'll see you in the next video. Bye bye.